card in Hong Kong. It is August 2024, and this is a step-by-step tutorial to create a waffle structure of a mesh or a sub-D object you have either created yourself or you found it somewhere on the web. And we use Rhino 8 in combination with Grasshopper. So we are planning to and execute an algorithm that will enable us to slice through an object and export these slices onto a plane and make it ready for laser cutting. So it is a like intersecting waffle structure you find in design applications, in architecture, but it can equally be an interesting thing to use in the production of sculpture. So we have Rhino 8 on a Mac, and I imported this pig's head in sub-D, which I made earlier. Again, you can develop something in sub-D yourself. There is a link to a very good tutorial below. If you have a mesh, make sure the mesh is closed and hasn't got a big patches of holes in there. So we start our grasshopper, and so this is the Grasshopper 8 that comes with a few new things. We start a new document, and the first thing we obviously have to do, we need to import our geometry. What we usually do, in the past we imported the mesh via mesh, but in Rhino 8 we have also a sub-D option, which we will use here. And these sort of simple operations should be familiar to you. I'll quickly save this. There's a waffle. In case we have memory losses on the Mac. So the first thing, we import this object into our grasshopper, and you should be familiar with this. So our node turns gray, and I go to my layers. I want to just remove this so that we only see what we produce in Grasshopper. So we have our object in Grasshopper, and the first thing we want to do is we want to slice this object in the X and the Y, and we do that with a node which is called contour. Okay, and we need to connect our sub-D to the contour, and you can it doesn't appear yet, but we also need to give it direction. Let's switch the display to full names here. Okay, so we have our shape, which we bring in here, but we need the direction, and obviously we start here with the direction of X. So we give the unit direction and a distance, and I go for a distance. Double click on your canvas. Let's do 40, which is equal to 40 millimeter. So our node turns green. The starting object here, when we look at this, is sort of around 300 millimeter high. So here you see the slices, and we do the same. We do the same in the Y direction. So what we can do is you can copy and paste this, but we do not use the X, we use Y, and plug that into our direction. And here you have it. And obviously here you can manipulate the distance of your individual slices. But I think 40 looked okay. So we have these slices. Okay. Now, what we want is to develop the intersection in between. So we go, this is how we do it. We need to, let's hide this for a bit. And we also hide this. So here we have our slices. And the first thing we want to do is we want to get the surface of all these contours. So we go to surface, and this is we take the boundary surface, boundary edge surface, and here we have them. And I do this first for the slices in the direction of X. What we want is we want to extrude it to simulate the thickness. So in this case we are using at the Academy, usually we are using a thickness of 3 millimeter. So we want to extrude it, so we, not a number slider, but extrude. So we have our base point here. And we want to give this a vector. For this we use an amplitude where you can plug in and you find the amplitude under vector amplitude. From here we can take our X direction, the vector direction, and plug this in here. And I think probably it always has as a standard set already number 1. So if we do this with a slider, you see the thickness changes, right? Now I don't use a slider for this. I use a panel, because this is something that it will always be fixed, and we can use it for the contours in the X direction as well as in the Y direction. So this is a fixed panel that represents the thickness of your material. Okay. Now, when you look at the contours, you see that our planes, the contour and the surface we extruded this from goes only in one direction. I want to have the thickness sitting nicely in the middle. So I do this, there are various ways to do this, but I'll do it in the following way. I want to move this. Type in move. So we have a move node, and I divide our amplitude by 2. So I halve that. Division. So I plug in my geometry, and I take my amplitude as a vector, and I take a panel and type in -2, half it. now you can see, I'm going to hide all this. So this is our 3mm board, and when we look at the contour, we have the contour nicely sitting, so it sits exactly in the middle. So this is exactly what we want. So we can do the same for the direction into the Y, and as we are working with code segments, we can now just copy and paste all of this but we do use the Y direction instead of the X. Hold on. We need to obviously, no, the contour goes in here. So, right. Okay, here we have the thickness of our material, it's the 3mm or whatever you use, and otherwise the rest stays the same. And I recommend you to sometimes just group certain items to keep your code nice and tight. It's also sometimes quite useful to name them. We can slicing segments. Okay. Now, obviously this doesn't work. We need to have intersections, cutouts that work like little slots where we can sort of slot these two segments together. And we do this the following way. So the first thing I would do is I take a cross-reference. And I flatten my geometries. So I literally just want to use the data that is the end result of this moving node. So we have our cross-reference here and here. So with a sort of clean data. And I do want to cut out the intersection of these two elements. I do that with a brep. That should be under the intersection here, and it's this one, brep. And here you can see this is the cross section from the X and the Y segments of this. However, if we look at it closer, let's just hide all of this. Just want to have a look. And some of these ones are not closed. They just take certain aspects. So the best thing you can do here, you put them into a bounding box. that should be, oh god, where is that? On the surface? Is it on the surface bounding box? Here, under the primitive tab, bounding box. Here we go. So, and this is the first set. I organize the second set in the following way. Again, I use a cross-reference. And I take the surface from here and stick this into A. What I'm trying to do is now, obviously I want to, if we look at our geometries here and here, what I want to do is I want to move these sticks halfway up the length of each individual slab, so to speak, so I can then cut these pieces out. So I need to move these upwards. I do this like this. I just want to have the pureless. I do it in the following way. I go back to my original surface. And again, I do a B-wrap in the intersection tab. And now I measure the length of the intersections here. Length. This should be on the curve, I think, analysis. Now, where is it? Here, list length, under curve analysis, right? So I take this one here, and if we stick a panel into it, I have all my panels here and the individual length. What I'm going to do is I'm going to move them upwards and half them. So I'm going to delete the panel. So move them into the direction Z, so I just take half of it, take a division, divided by 2. To get a quick panel, this is something perhaps you need to remember. You double click on the canvas, double slash, and you have automatically a panel. So I divide this length into 2. And I move my box half the length. All right, so I have them halfway up now. And I do that, I need the cutouts on the lower part as well. So I do another motion, move. I take my boxes here, and I take the same algorithm, but I negative. Here, I go at a negative value into it, so I have these ones now up and down, so I can extract them now. So now all we need to do is do a Boolean difference. We go back to our intersection, we take a solid difference, which is a Boolean action, flatten this. And we take our initial curve, our initial extrusion, and I'm running a little bit out of space here. You can see everything, so I take my geometry from here. Here we go. And I take the geometry out. And you can see I've got now my slabs cut out. If I hide everything. So here you can see the cutouts. And I do this the same. For the lower part, I take solid difference, flatten the second B-wrap, and use the lower extrusion. I can get everything in here, so it's this one. Okay, so if we hide this one, so we've got the cutouts on the bottom, and the cutouts on the top. Right? So they slot into each other. So what I'm going to do is just group these together and call it slot cut out. Again, it's always very useful to organize your code and to name parts and take notes in case you will build up over the years a large number of Grasshopper code if you're getting into this, and it is useful when you open some old scripts from 1 or 2 years ago. When the code is nicely organized and labeled, it's much easier to figure out what's going on and where the parts are you might want to copy out or work on. So now what we could do here, theoretically, we could bake this and then project it onto the ground plane and take the with the make 2D option in Rhino. But so the next thing we're going to do is we project these outlines we have here So the edges, we want to select them and project them onto the ground plane. So, and we do it like this. Okay, we'll leave this on for now. Okay. Okay. I again go to my surface tab and I deconstruct the B-rep here, where we get the faces, the edges and the vertices, and I analyze the area of the faces. So you type in area, and here you can analyze the faces, and you get center points. I want to sort this list from big to small. Take the area of the faces, and sort this list. With a list item. Again, something you will use an awful lot. But I want to list them from large to small, so I will reduce or reverse this list. So I start with the biggest and then this kind of moving down to the small. And I take the edges and connect them via the join curve tool. So I have naked edges here and I'm going to connect them, right? And the way we flip them onto the ground plane, we take our B-rep and I want to analyze the surface via the vertices and fit those vertices to a plane. And these planes I project or flip over and orient to the ground plane. So planes are here. So in here we have the plane fit, and we use where's the orient plane? Orient. This one. What is it here? Under vector. Wait. I'll need to figure that out later. I just use the type. So I take my geometry as the curves and I have the planes here. You can so see them lined up. And this projects these onto the ground plane. Now I want to spread them. and I do that with a list length. I flatten the input. I just take the curves as a bare list. I want to move them. So I take these objects, the geometries, only take the geometry without any backlog, and I want to move them by the length of this list from small to large. I move them via the x-axis. And I'm using a series. And I count the length here, take it from here. And take as steps 200 millimeters to start from. And here you can sort of see. Let's blend everything out. So here we have them projected onto the ground plane. I group this. I can project to plane or ground. So for the lower part, I do it slightly differently. Let's line this up again. So this is for the distribution, the y-axis, and again we go to our surface tab, we deconstruct our B-wrap, take the area, again we take the faces and sort the list, big to small. And here again we need to reverse, so we have the bigger first and the smaller at the end, and we list these items. And as for the surfaces, this time again we take the B-wrap edges and join them. So you can see the curves. And now we want to flip those. So we again deconstruct our B-wrap. Again we take the faces and take the area. So you can see the center. And we construct a plane to those. Again, this should be under the plane vector. So we take the centroid, stick them into our origin, and orientate the y-axis to the z. And again, we orientate this one as a source. Take the curves of the geometry, and we have them now on the ground plane. Again, we need to spread this, so we do the same as we have done here, but we could possibly just copy all of this. That's what we need. Hold on. Now we just go this, 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 and this, and this. Copy and paste it. But obviously we take the curves from here and geometry from here, but do not use the X, we use the Y. And here we have them nicely displayed on the floor. And I sort this out, and then we finish the job. So I have cleaned this up. So we have the X and the Y, and we have the individual geometries here in the X and here in the Y. And what we want to do is we want to pack them into a tight space so we can actually get them into a laser cutter. So here we use a merge node and join these two geometries into one. And whenever you use a merge node, I recommend to flatten the inputs. And now we pack this together, and this is a little snippet I got from something which is called Open Nest. Open Nest is a plugin you can get via Food for Rhino, so please sign up if you haven't. And it's a very useful thing if you want to do a lot of laser cutting and layout of shapes on ground sheets and, or boxes as well. It's a very good orientation tool, makes things, workflow very efficient. So this is just something I got from Open Nest, and I literally just repeat what I got. So we have our geometry, so our shapes, and in Open Nest it has something like this. So we can pack our geometry, but it asks us for input of a plane, and so we use an XY plane. But we get a warning, so this doesn't work. So we need to list these in its length. So these curves we get, and we use a repeat pattern, a repeat data pattern. And we plug this into the plane. And we have now all these shapes neatly lined up. To finish things off, I quite like to, or it's sometimes useful to highlight thicknesses of curves. And in Rhino 8 we have a few more options now. Under the display we have not only the custom preview, but we have also custom curve preview. So this is a new node, and for this you need to use this in combination with model line type because it asks us for a line type. So we have our geometry as curves. Let's just blend everything out here so we are not getting confused. Here we go. And we can give this a color with a swap. Hold on. I'm going to plug this in there. Give it a nice blue. And we can give this a width of 1 point, let's say 6. Give this a slider. And it also asks us for a name. Again, double slash. We have a panel line thickness. And we give this as a name. Oh, it doesn't like. What doesn't it like on this panel here? Nah. Line type. Does it like it now? Yeah. And here you can sort of see if you can thicken this up. Sometimes if you want to, you know, visualize things for you, and you have many pieces, sometimes I find this quite helpful. So, and here we are. Okay, so let's quickly go through this. So again, we can switch this on. So from our sub D or mesh, we make slices in the X and the Y. We take the geometry and cut out these slots where the intersection of the two X and Y panels happen. We make the cuts. We take the edges of these cuts and project them onto the ground plane. And then we just rearrange them on the ground plane. And make it. So whatever you use this for is obviously entirely up to you. We will use it in my class to make sculptural objects in the upcoming class, but you can apply this method to, you know, many other fields, be it design, fine art, or architecture. Okay, I hope this was helpful, and I see you next time.